So here I am going to discuss certain optimization models in economics. These are not the only models, but certain ones which we would focus on. Uh, and I should have read. I do not know why I cut off the constant optimization uh, term. Because at the end, it is largely you have constant optimization problems. There are very specific problems, and economists always look at maximization problems. Most economics books, if you open, they would consist of maximization problem, maximize something subject to some constraints. So what happens here? But here we will begin with a model which is very important in finance, for example in portfolio optimization, for example. In utility maximization problem. These kinds of, or kind of profit maximization problem. So we will start with a structure which is very simple. So we will talk about two basic models, P1 and P2. So P1 is the maximization of the function fx subject to these constraints gix greater than equal to 0 and x is greater than equal to 0. So those x's which satisfy these constraints means for all the i's it should have gix equal to 0 and x must be greater than equal to 0, means x is element of Rn plus. And fx is usually a concave function. It could be profit maximization, it could be utility function, and many other things. But it always need not be a concave function, it could be just a differential function. But let us assume the most simplest structure. It has a concave function. So it is the same structure as the old part that we learned in two classes ahead, that is max of fx subject to x element of c. In this case, the set of c is a collection of all x in Rn for which gix is greater than equal to 0 for each of these i's and x is in Rn plus. So that's what the feasible set is. So the feasible set is basically can also be viewed as the intersection of two sets. One is say F1, or which is the set of all x in Rn for which gix is greater than equal to 0, intersection with Rn plus. Now anyway, this set that we get is a convex set. So you're maximizing a convex function over a convex set. So this is what constitutes, at least in the eyes of an economist, a convex programming problem. Mathematicians obviously talk about minimizing a convex function with respect to convex inequality constraints. We will look into it later on. So there is a mistake here. It's not Rn plus plus, it is Rn plus, because x is here greater than equal to 0, not strictly greater than 0. Whereas strictly greater than 0 means all the components are strictly greater than 0. Here's a small mistake. It should be Rn plus and not Rn plus plus. The set C1, as I told you, can be given like this. Of course, you can prove that to be a convex set. Here also I have made a mistake. This inequality should be greater than equal to 0. This should be all greater than equal to 0. So here I have made a mistake because this is a concave function. So please correct my mistake. All these inequalities should be greater than equal to 0, which I have by mistakenly written less than equal to 0. This is what happens. Here is a mathematical optimizer trying to talk about his subject to people who are principally in economics. I am this whole idea of talking about minimization of convex function over convex sets. This is completely ingrained in my psyche, that trying to write maximum problem, maximization of something, sometimes feel very alien, though it's the same subject, same structure, no great difference about it. Though, so it's suddenly you feel kind of an alien thing, that okay, oh my god, I might be making mistakes, and that kind of mistakes actually creep up because your mind is filled with convex function. You forgot that you are talking about concave functions. So it must be slightly humorous, but that's a part of doing things. See, I just want to tell you, when a subject gets into you and the way you get into a subject, it gets so much ingrained in your psyche that you're talking about the same subject with a slightly different representation. You might just make mistakes when you write. Okay. So you can change this with equalities because that is what the definition of concavity is, and that's what it means. So because this is a convex set and Rn plus is a convex set, the intersection of two convex set is convex, so this is convex. So you know the utility maximization problem. So if X is a commodity vector, so there is some notion of preference which we have not discussed in this course. So if you have two commodity vectors or two commodity bundles, if you want to say X and Y, a very important idea of economics is preferences. So if I give you two commodity bundles, you might be able to tell me that you prefer X over Y, or you prefer say Y over X, or you are indifferent. It doesn't matter whether you take X or you take Y. So, but these preferences is a very qualitative way of looking at things. There is no way to numerically, when you look at it, to numerically substantiate what you are saying. That okay, I prefer X over Y. Okay, yeah, some feeling why I do it, I do it. But it is important to know that why X makes you more happier than Y. Why having X you seem to be more delighted than having Y. So something, some numerical function might measure your kind of happiness or utility. So which means if X is preferred over Y, the commodity bundle X must be of higher utility to you than the commodity bundle Y. So when X is preferred over Y, then the utility of having X is obviously greater than, numerically greater than the utility of having Y. So there's a whole subject of how utility functions are constructed and why various approaches are taken. So that's a whole gamut we will not get into, because here essentially we are looking into how to apply things to several problems and not exactly why. We are not getting into hardcore economics here. Here the math is there, the analysis is there, the optimization is there, and then we are looking at optimization problems. So what you do, what you want to do, you want to maximize your happiness, suppose your utility. So you want to find a bundle X which maximizes your utility. At the same time, you have to understand that bundle is bought with some cost P, and you know that the total cost that you pay for the bundle cannot exceed your budget, which is Px less than equal to B and X greater than equal to 0, which can be obviously put back into this particular form. So here is a single function g1x greater than equal to 0, and this is a concave function. Why? Because this is a constant minus a linear function. A linear function is both convex and concave, so it's a concave function. Minus p of x is a linear function and hence a concave function. So this is a kind of but in many cases in economics we might have to deal with a situation where I max a convex function fx over gix less than equal to 0. Okay, this is a very important situation where I am here, the function f might not be even convex. So I am maximizing a function subject to say gix less than equal to 0, where gi's are convex functions. Okay, let me see what is an example of this. These kind of examples comes into the issue of production. Suppose there's a firm which wants to produce say n quantities, produces n different type of things, and it can produce every one of them in certain amount, say first one in x1 amount, second one in x2 amount, and so on. So there is a notion called production function. It tells you that if you give me the input x1, x2, x3, xn, this is the input that you give. For making the first quantity, you give an input x1. For the making the second quantity, you give the input x2. So this is the amount of raw material, labor, capital, whatever you have given an input. All those inputs that you give. So let me get back to this one second. So production function tells you that okay, maybe forget just not n quantities. Maybe it's better to look at one quantity. I think I just to you off the track. Let us look at just one quantity. I'm sorry, one object that you are making of a form. Now suppose to make that I have n different inputs. It could be labor, it could be technology, it could be capital, blah blah, many things. So you have n inputs which are given by 1 to n inputs, and each input you give in certain quantity x1, x2, xn. And once you put in that input, you know that the input should act together in such a way to tell me what is the level of production I am doing. Now each of these inputs have a cost. Labor, you have a cost. Technology, you have a cost. For the initial capital, you have some capital. There is a cost. So many other things is a cost. Maybe electricity that you need is a cost. You need some water supply, that is a cost. You need to maintain an infrastructure which can come under the capital, of course. That has a cost. So all of these inputs have some unit cost associated with it. So which are the positive numbers W1, W2, Wn, and these are often called factor prices. So what I have to do, I need to maximize my production. So any firm would like to maximize the production such that maximizing the production such that W1 x1 plus Wn xn, this quantity is less than equal to k. That is, the total cost that I am putting in has to be below certain thing. So this is the maximum amount of money I can spend, k. It cannot be more than k. I would love to have it less than k. Here x size are actually strictly bigger than 0. You cannot, if you are producing 0, if you are giving, you cannot give 0 input to things, because these functions are, then you cannot produce the object. The object needs all these inputs. You cannot say, suppose I think of a firm just talking about capital and labor. So I have to give positive capital, positive labor. If I give nothing, then there is no production. So which means these xi's are all strictly greater than 0. The trick here in the constraint case is also just what we had learned, that when you have these non-negativity constraint, this x greater than equal to 0, or x element of Rn plus, is often called as a non-negativity constraint. So whenever we are speaking about the non-negativity constraint, please understand that whenever we have xi strictly greater than 0, that is absolutely the positive constraints, then it is clear that this xi strictly greater than 0 can be totally forgotten about from the point of view of optimality condition, and that is what we will start discussing right now. That is, if you just put the problem in up to this part and forget writing this, you write the same optimality conditions and get the same solution. Actually your solutions would come out to be positive. So now this kind of this kind of things is pretty simple if you look at it, because there is just one constant here, of course, but and I'm saying that you can throw it off. Of course, it looks very same, but it can be also put in a certain different way. You can say, okay, I want to minimize my cost, but maintain a production level. The production level should be equal to y naught, or production level should be greater than some equal to y naught, where x is strictly greater than 0. See, it's so what happens, this problem that you write, if you forget the xi strictly greater than 0, is of this form. While here you can also have a problem, this function fx could be non-convex, non-concave, actually very highly non-linear, non-concave function. So when you are maximizing, then things might not be so simple. But here you have a non-concave constraint, so I can have this to be strictly greater than 0, because you want a minimum production level, at the same time want to minimize the input cost. So this same problem can be either viewed as a minimization problem, the same issue of production, and the same problem can be viewed as a maximization problem. That is what we saw that the same problem can be viewed in either way. So as we are writing that, we want to assert here that when we have strictly positive decision variables, then from the view of optimality condition, this problem can be viewed as if there is no restrictions on the variables. So let us see how do we do it. There is a little bit of the page problem. Page has a problem in the sense that some page, this page should have been scanned after this page. So basically now we are looking at a situation, if you look at the production maximization problem, we are looking at a situation where you are maximizing a function fx where x element of C intersection Rn plus. Now C is a closed convex set, but C intersection Rn plus plus is not a closed convex set in general. Please understand that. Just draw a closed convex set, take the unit circle and shade it, everything inside the unit circle. Say x square plus y square is less than equal to 1, the ball. And then intersection with Rn plus plus. Then the part of the axis part is not part of that intersection set. So that hence it doesn't form a closed set. It neither forms a open set either, but not forms a closed set. So we cannot apply the standard result. We cannot, how do we compute the normal cone? Because we have not defined the normal cone for a closed set. This thing actually now motivates us to think whether, forgetting what we have got from the geometrical structure of projection, unique projection on a convex set, can we think of defining the normal cone for any convex set? Just give a mathematical definition. Just bring that definition, what you have done for a closed convex set, and bring it up and push it, throw it on any convex set. Can that work? The answer surprisingly is yes. And this definition actually provides is a very good fodder in the fact then it makes life very, very simple. And after writing the definition for any convex set, so we had taken any convex set, a normal cone to C at x star, where x star is in C, not Rn. I made a mistake here. It should be x star is in C. Then NC x star is a set of all V for which the vector V makes an angle, makes an obtuse angle with the vector y minus x star. The inner product is less than equal to 0 for every y in C. This is just that same definition, but just turned on for a single just a convex set. It could be open, closed, doesn't matter, anything. If obviously if x star is not in C, we will define NC x star to be an empty set. Now using proposition 1, of course we can say that NCX is equal to the 0 set, just a trivial set containing 0 for all x in C when C is an open set, because every point is now an interior point. So we can just use the same type of proof to prove this, to do this, what we have done in proposition 1. So what happens is that now theorem 1 also, you see the whatever we have studied in theorem 1, if we instead of a closed convex set, if we have taken just a convex set, the same story can go through without difficulty. You can try to work them out and see that whole story goes without any difficulty. So hence we have to do something. So now we have to, now we know that, let us look at the theorem 1 where whatever be the convex set C, I can just get on with my life. I can just get on with my life and I can write the same theorem 1 throwing out the closeness assumption for any convex set. So if you write down the definition, if you write down the proof, if you see the proof, nowhere the closeness of C had been an issue. Because at the end we just, because what we proved that gradient of fx star x minus x star is greater than or equal to 0 for all x in C. So negative of the gradient by this definition that we have defined is element of the normal cone. So the closeness issue was not a very big issue. So you might be wondering why I didn't do it right away when we were defining the normal cone. I didn't do it right away when we were defining the normal cone and also in the beginning of this chapter or this lecture. In the sense because we want to keep a feel that the idea of normal cone is basically a byproduct of the idea of projection, which it is. But then as we require, can we be more Can we do the things much better? Can we relax the closeness idea and gradually go towards building a kind of calculus of normal cones? So now the question would be, so my practical problem has now put me into this situation where if you look at my problem P3, which was the problem this one. So the optimality conditions that I would have here is of this form, because again we are maximizing. Now C is a closed set in this particular situation. Now there is an important result from convex analysis. Okay. It says that if C1 and C2 be two convex sets, and X star, they are not telling closed convex sets, please understand. And X star is in C1 intersection C2. Then if I have the following condition holding, this is sometimes called a qualification condition. For some nice thing to happen, something has to be checked or be verified before. That the normal cone to C1 at X star intersection, the minus normal cone to C2 at X star, the intersection must be only the zero element. It could be a reverse also. You can take minus NC1 X star intersection NC2 X star would be zero. It doesn't matter. So the intersection of one of the normal cones with the negative of the other normal cone can have no other element other than 0. There cannot be any other element. The intersection is a singleton. Then the normal cone to the intersection of these two convex sets at X star is nothing but the Minkowski sum of the two separate normal cones. That is, normal cone to X star to C1 C2 at C1 intersection C2 at X star is the normal cone to C1 at X star plus, but there's a Minkowski sum with the normal cone to C2 at X star. So you take a V1 from X1 and V2 from V1 from NC X star, NC1 X star, and V2 from NC2 X2, and you add them V1 plus V2, you will get an element here. That's it. So I'm not getting a proof here. The proof is pretty complicated because I am trying to make this notes into a kind of book. So there I'll try to see what is the simplest way to do the proof of it. There is a much advanced way to prove it, which I don't need to show you here, and I'll not even write in the book. For economists, don't need to bother with those mathematical complications. But this theorem is important because at the end, in the next classes, you will see we will talk about a very when we will describe C with certain when I'll start describing C with good amount of constraint, we will have equalities and inequalities describing C, just as we had done here. Then it will be very important to finally write those optimality conditions. It will be very important when you want to study Karush-Kuntagar conditions, the famous KKT conditions. When you want to do that, this result would play a very crucial role. So it's very important not to forget this result. So what happens if this happens? In this particular case, when you have written grad fx star is element of normal cone to C intersection Rn plus plus 0, you see NC x star intersection minus Rn plus plus star, automatically the qualification condition is satisfied because Rn plus plus is open set, so this is 0. This is 0, and hence NC x star intersection 0 is just 0. So the qualification condition holds, and by what we have learned by theorem 6, so this intersection is nothing but NC x star plus n Rn plus plus x star. But n Rn plus plus x star is again 0. So this intersection, this normal cone to this intersection x star is same as the normal cone to C at x star. So our condition, this condition that we had got, this condition A now reduces to the condition that we had in theorem 1. So this is nothing but the optimality conditions that we had, subject to x element of C. Yes, C is a closed set, of course, I mean in our actual real applications. So because if you see, for example, let us see with this. Where is this example? For example, this one. You set the set of all x1, x2, xn in Rn such that this is true by the continuity of this function, because this is linear function. This is nothing but inner product of w and x. So that is again a closed set, which you have already learnt in your first chapter, these kind of sets. So what we have got, that again the optimality condition is same as that of the original, the one which we have studied uh, in theorem 1, the basic problem max of fx, or theorem 1, or the problem 1, whatever you want to say, the max of fx subject to x element of C. So this is, so from the point of view of optimality condition, when you have an open set as one of the constraints, or strict inequalities as as the functional constraints, you can just forget about them. Or if you have something like xi strictly, strict inequality is not strict inequalities of the form xi greater than 0, not all strict inequalities. So if you have an open set, you can definitely forget about it, because of whatever discussions we made here. So if your final feasible set is made as the intersection of C and an open set X, a closed set intersection with open set is your final feasible set, then you can actually forget about the open set completely. So from the point of view of optimality conditions, if there's open set, you can forget it. So if you are writing your final feasible set is the intersection of a closed set and an open set, just keep the closed set, forget the open set. That's the idea. Now in finance, for example, this kind of problems where you minimize a convex function with respect to convex inequality constraints and affine equality constraints. Affine functions are linear functions plus some translate some number. So this is what happens with this is exactly what happens with problems in finance. This is the standard structure of problems in finance. Portfolio optimization problems, for example, would have a structure like this, right? Okay, so let's now this is a uh, very particular structure, because we are imposing convexity assumptions on the function. But economics, finance, largely convexity would creep in many places. But from a point of view of optimization, a very general form of minimization problem would be a problem like this, where fx is a finite valued function, gix and hx are just functions. You don't have any, you don't bother about any restrictions on them. And this x element of x, this kind of restrictions are often called an abstract constraint. Obviously, in most cases in economics, x is Rn plus, but doesn't matter. The story for this is called the natural representations of the general form of a functionally constrained optimization problem of the minimization type. And here it is of the maximization type. Obviously, I forgot to write here I equal to 1 to m and j equal to 1 to k. This is what happens when you're writing. When you type, you're slightly much more cautious about what you're writing. Unfortunately, forgive me, I didn't have much time to type as your course time was coming down. So but if you have the same feasible set, suppose you have the same feasible set, then minimizing or maximizing a problem is not a big issue, because at the end, what happens if the feasible set remains same, then minimizing a function over a set C is same as maximizing the negative of f. So minimizing a function f over a set C is same as maximizing the negative of that function over the same set C. And when you take the compute the value, you whatever max value you get, you take the minus before that, you take the negative of that. So if there is a maximizer of minus fx, the same x star, if that is the maximizer of this problem, will actually minimize this problem, will be the minimizer of this problem. So with this we end our discussion, and again in the next class we will talk about actually going into the Karush-Kuntaker condition, which lies at the heart of optimization and used repeatedly in economics. Thank you very much.